Good evening. I'm Brad Story, Associate Dean for Faculty Affairs in the College of Science. I'm standing in tonight for Dean Garzione, who unfortunately caught a bad bug and was not able to be here tonight. So hopefully she'll be back with us next week. So thank you for joining us this evening for opening night of the Surprise Twists That Transformed Science lecture series. Before introducing the lecture, please join me in giving tonight's musicians, Jake O'Rourke and Daniel Woodruff of the Desert Music Project, a big round of applause. Thank you. In the spring of 2006, the College of Science launched its first public lecture series on the topics of evolution and global climate change. Bringing together educators and researchers from inside the college, the series was received by audiences that have grown in size and passion for science ever since. I hope you will continue to join us on Wednesdays throughout February as our speakers share their research and the twists and turns that the scientific discovery process often brings. Now I'd like to take a moment to recognize the Galileo Circle members in the audience tonight. The Galileo Circle is a valued community of individuals whose support is vital to the continued excellence of the College of Science and the University of Arizona. Thank you for your continued support of our students, faculty, and staff, and for being here tonight. If you would like to learn more about becoming a Galileo Circle member, please see the friendly faces in the lobby on your way out this evening. Now I'd like to thank the lecture series corporate sponsors and media partners, in particular our presenting series sponsors, Halewa Companies, Raytheon, and the Research Corporation for Science Advancement. Our series sponsors, the Marshall Foundation, O'Reilly Chevrolet, Tucson Electric Power, TMC Health, the University of Arizona Research Impact and Innovation, Tech Launch Arizona, and Visit Tucson, and also our media partners, Biz Tucson Magazine and Cox Communication. I would also like to give a big thank you to Arizona Arts Live for their partnership in bringing the lecture series to life in Centennial Hall every year. I am pleased to share that the College of Science is collaborating with the University of Arizona Poetry Center once again this year for the lecture series. Before each lecture begins, a poet will read an original poem that has been crafted specifically for the topic of the lecture. Tonight's poet is Julie Swarstad Johnson. Julie is the author of Pennsylvania Furnace, the editor's choice selection for the Unicorn Press first book series, and co-editor of Beyond Earth's Edge, the poetry of spaceflight. She has served as poet in residence at Lowell Observatory and at the Gettysburg National Military Park, which led to the chapbook Orchard Light. She lives in Tucson and works as an archivist and librarian at the University of Arizona Poetry Center. Julie, the stage is all yours.
Thank you so much, and good evening. It's good to be with you. The title of this poem is Interference Pattern, which I think you'll hear more about this evening. But the brief version is that an interference pattern is one way that we can see that a gravitational wave has passed through. This is interference pattern. I have known nights so dark, I could not find my way among the stars. Cold lights clustered thick, constellations slipping through the mind. Far out in that bright darkness, two nothings merge into nothing. Two densities unimaginable except in numbers, two unavoidable future points, two enigmas far removed from us in time spiral and collide, become another black hole. And here on Earth, we feel it, not in our flesh, but in our senses extended into lasers and vacuum tubes miles long that catch a ripple in space-time slender as memory, and the instruments tell us something has passed through. We have always lived on this shoreline where waves roll over us and never return. High in a mountain canyon, a jaguar slips past and leaves a flash of black rosettes, dark circles and dots like a melody inked across a page. Unheard, unseen except by the camera's inhuman eye, this song surrounds us. Like a stone, the pattern lives in the mind, and the mind, unstoppable, surrounds it, remade around that shape it catches on, only as it sweeps beyond. Thank you.
All right, thank you, Julie. Your poem perfectly set the stage for tonight's lecture. So I would now like to introduce tonight's speaker, Sam Gralla. Sam joined the College of Science faculty in 2015 and is an associate professor in the Department of Physics. His research explores the physics of strong gravitational and electromagnetic fields, as well as the associated astrophysics of black holes and neutron stars. If Sam's name sounds familiar to longtime supporters of the lecture series, well, you're right. He gave a terrific talk in the 2017 College of Science Rethinking Reality lecture series. We are excited to have him back again this year. Please join me in welcoming Sam to the stage.
Tonight's story is a battle. And the first battle is between me and the slide projector. What every performer wants to hear. We're having some technical glitches. So let's get a little warmed up and think about gravity. Gravity is the force that is keeping you in your seats right now, listening to me. Gravity is the force that is keeping the Earth on its orbit around the sun. Gravity is the ubiquitous force by which everything in the universe attracts everything else. Today I'm going to tell you about a competition between, on the one hand, gravity, and on the other hand, everything else. Any kind of matter that you could think of, or that AI image generator could think of especially, any kind of force involved in the description of that matter, any kind of theory of physics you might learn about in a class, all of that is pitted against gravity. Now, these little battles are going on all the time. Right now, you're sitting in your seat. If gravity had its way, you'd be going right through to the center of the Earth. That's the strongest gravitational force on you by far. But your chair has other ideas. Your chair is pushing back up and keeping you there. Your chair is winning the battle. Or at least it's a tie. Now, our lecture series this year is about surprises, and there's going to be a whole bunch of them over the next 4 weeks. The central surprise today is that sometimes gravity wins, not your chair. Now, what would it mean for gravity to win? Well, I guess you're going to the center of the Earth, but so are you, and you, and you. We all are. If gravity's winning, Centennial Hall is going to the center of the Earth. The whole Earth would be collapsing under its own gravity. That's what it would mean if gravity overpowered everything else relevant for the Earth. What would this imply? Thankfully, it won't happen for the Earth, but let's imagine it's happening for this blue blob of matter. This blue blob of matter has gotten so big, it can't hold itself up anymore against the gravitational forces that want to crush it. So it's going to shrink. Now, when this happens in nature to a star, it's over in an instant. But we're going to show you slowly here. Imagine you're on the surface of this blob. Gravity is getting stronger and stronger. Why? Because you're closer to all that matter. It's gotten smaller and you're next to it. Gravity's getting stronger. You might want to think about leaving the surface. In fact, you don't have too much longer before no rocket ship you build could possibly let you out of this gravity. By solving Einstein's equations of general relativity, we know that at some point, an event horizon forms. And that means if you go inside that red circle, you're not coming out. And you're not telling your friends either. Your cell phone signal's not getting out. Nothing is getting out. Light is not getting out. And that's why we call this object a black hole. Now, what happened to all that matter that fell in? Well, here I have to be honest. We really don't know. We can use those laws of physics to study that matter down to the very tiniest possible scales we can conceive of, but then those laws of physics say infinity. That's not a good answer. So we hope there will be better laws of physics someday that will answer the question of what happened to all that matter that went in. But I'm here talking to you because, beautifully, with black holes, we don't care about what went in. By definition, nothing inside can affect the outside. It could be flying unicorns in there. It wouldn't matter from the perspective of physics outside. And so people like me can have a career studying these black holes. I'm going to tell you the whole story of black holes today, how they were conceived of, discovered, and ultimately how their study changed the way we think about reality. I mean that. And I'm going to start in the Industrial Revolution. James Watt made his celebrated improvements to the steam engine. This device was practical. It was transforming society. As we move into the 19th century, Sadi Carnot is studying the upper efficiency limits of steam engines. How good can he make these steam engines as an engineer in the army in France? And he's discovering a new science, the science of thermodynamics. Thermo for heat, dynamics for motion. Now, there are 4 laws of thermodynamics. Not going to go through them, but remember there are 4. That's going to matter. And the most familiar one and the most important for our story is the law of conservation of energy. Energy is neither created nor destroyed, only transformed from one form to another. You may have studied this law in school, but actually it's quite familiar, I would hazard a guess, even to the non-physicists in the audience. We think about energy, right? We have to pay for it. We hear about all the different kinds of power plants that, help it come to us by electricity and so on. It's in our vernacular that energy is a thing. But in the 19th century, this was a radical new idea. And like many great ideas in physics, it opened as many questions as it answered. And so these folks now had to answer questions they didn't have to think about before. For example, what powers the sun? One could no longer say, as the ancients had, that the fixed stars are just out there rotating. One had to think about the power source. The sun's making all this energy. Where does it come from? And the same man who had discovered conservation of energy, Julius Mayer, gave us the first theory of what powers the sun. And it was asteroids smacking into the surface of the sun. I bet you didn't know that. But you see, he's thinking, well, it can't be coal. It can't be the stuff we're used to. The sun is just so bright. What could it be? Well, an asteroid, as he's pointing out in this quote, if it gets going really fast from the sun's strong gravity, can transfer heat to it. That wasn't a great theory, but it was refined. And what came to be accepted was not asteroids hitting the sun, but the outer layers of the sun hitting the inner layers of the sun. This gravitational contraction that we just talked about was believed to be the power source of the sun. They thought the sun was gravity-powered. Now, this is not the correct theory of the sun. We know now that it's powered by nuclear fusion. But I bring this up because this mechanism is going to make an appearance in our story. With the realization that the sun had a power source came the realization that it wouldn't last forever. And so one had to think about what would happen when that power source ran out. It made it into the poetry of the era. Tennyson beautifully writing, "The moonlight is the sunlight, and the sun himself will pass." And of course, it made it into the science of the era. And a hint came from observations as we move into the 20th century, with the star Sirius, the brightest star in the night sky. If you have good eyes, you'll see in this modern picture of Sirius that Sirius has a companion. There's Sirius A, the main one, and you might just be able to make out Sirius B. This much smaller, fainter star was discovered in the early 20th century, and it was called a white dwarf. And that name came from the fact that it was small, but the thing is, it had a mass similar to a star. It's like the size of the Earth, but it has the mass of the sun. That's an incredible density of matter. There's an easy way to remember this. It's 5 tons per teaspoon. If you could take a teaspoon of white dwarf matter and hold it up, you'd be holding up 4 large rhinoceroses. Fantastically dense, a shock to everybody, but also a great discovery, and it gave a hint about the fate of stars. The theory went that when a star runs out of fuel, it would start this process of collapse. The fuel is no longer holding it up. The gravity pulls it down. It collapses. And then at some point, you form this new kind of high-density matter, 5 tons per teaspoon matter. That stops the collapse. Matter wins. And we have a white dwarf. Problem solved, right? Well, enter a young Subramanian Chandrasekhar. He calculated that this white dwarf matter people have been talking about, it's not quite strong enough. You see, this matter was new. They had to use the new laws of quantum mechanics to understand it, and the first calculations were crude. Chandra's calculations showed, okay, it's okay for the sun. It works for Sirius B. But if you had a star much more massive than the sun, say twice as massive or more, the white dwarf matter would never be able to stop the gravitational collapse. Now, Chandra, for his part, viewed this mainly as a prediction. He said, okay, you're not going to see any more white dwarfs that are too massive. There'll be an upper limit on every white dwarf you'll ever see. That prediction was verified, and in fact, he got the Nobel Prize for that work. But for our story, we have to talk about the other man on the screen, Arthur Eddington. Eddington was the senior astronomer in England, maybe the world. He was an expert in the sun, and he was also an expert in Einstein's theory of gravity. And so he thought about the gravitational implications. He understood that if the white dwarf matter can't oppose collapse, a black hole will form. He really did. He didn't say black hole. That term hadn't been invented yet, but he writes about the star cutting itself off from the rest of the universe. And let me tell you, Eddington hated this idea. He thought it was absurd. And famously, he gave Chandra time to speak, extra time to speak at a meeting of the Royal Society, and then got up afterwards and started attacking Chandra's ideas, saying it would predict this crazy thing about a black hole. And it's such a shame because Eddington was most equipped of anyone to figure it out right then and predict black holes. But he hated the idea so much. Instead, he chased after mistakes in Chandra's calculation, and there were none. Chandra turned to other topics, didn't come back to gravity for decades. Maybe he was turned off by the encounter. But unfortunately, at just the moment when black holes could have been predicted, we have a bit of a lull in the science of black holes. With no one really to pick up the mantle, there was about a 30-year break, some bright spots in there, but about a 30-year break in our story. And I'll pick back up in Poland in 1962. This was a truly international meeting, despite the ongoing Cold War. In the bottom of your screen is Soviet physicist Vitaly Ginzburg. The West was also very well represented. And I'm going to focus on a young American particle physicist, Richard Feynman. If you've read Feynman's books, you know that Feynman was always up for a bit of fun, and up there he's playing hopscotch. The person he's playing hopscotch with is Ivor Robinson. What I want you to remember about Ivor Robinson is he's from Texas. That's it. Now, Feynman was a particle physicist, an outsider at this meeting, seeing what was going on in gravity, and boy, was he unhappy. Feynman wrote this amazing letter, which is not polite enough for this esteemed venue, too impolite for this esteemed venue. I encourage you to look it up. More or less, he said, there are no experiments, and so this field is a disaster. And he says, oh, one guy gets up and he writes these equations, and they're obviously wrong, and this other guy gets up and writes these right equations that are boring, and a third guy, they start arguing, and remind me not to come to any more gravity conferences, he says to his wife. So, you know, Feynman is perhaps being a bit harsh, but he does have a point. I don't know which caused which, but during this 30-year lull, the relativity, the theory done by relativists after Einstein's equations of relativity, was very separate from the observations done by the astronomers. There were no experiments in the field of gravity. Well, all this was about to change. 1 year later, we had a spectacular discovery. Martin Schmidt was puzzling over these objects that were called radio stars. They looked like stars, but they made a lot of radio waves. And he made the breakthrough in realizing that these objects were actually really, really far away. A mental block had held sway. People kept thinking of them as local, and they made no sense. He realized they were really far away, as far as a galaxy. And then people went back and looked at this particular object, went back and looked at photographs of this object taken by amateurs over many years. And they found that this object, this 200 billion light years away object, was changing its brightness over timescales of like a year or a month. Now, very big objects don't change very quickly because one side of the object might start heating up due to some effect that makes it brighter, but it takes time for that to propagate across. The fastest it could happen is the light travel time across. So we have an object that's brightening and dimming as rapidly as a month. That means it can't be bigger than a light month, which is absolutely tiny for something as bright as a galaxy. This object was brighter, in fact, than any known galaxy at the time. But it was tiny. It was 1 million times smaller in radius or 1 trillion times smaller in volume. Think about that. The light of a galaxy, normally 100 million stars or so all emitting, is coming from a region 1 trillion times smaller. What in the world could this quasar be? And now we're back to the same situation. In the 19th century, what powers the sun? Now in the 20th century, what powers the quasar? Now they had Einstein and they had his equation, E equals mc squared. If you have a mass m of fuel, then you can get energy equal to the mass times the speed of light squared out of that fuel. Now, if it's Star Trek and your fuel is half matter and half antimatter, you can get all of that E equals mc squared energy. It's very useful. In the real universe, we don't have much antimatter at all. This is definitely not what powers the quasar. So we're talking about some efficiency factor. So you go through the fuel sources you know about. Could it be chemistry? Burning coal. Well, that didn't work for the sun. It's definitely not working for a quasar. What did work for the sun is nuclear reactions. That is actually what's powering the sun. Those are much more efficient, but it wasn't really going to work for the quasar. Marginally, you could get enough energy out, but you'd need like 1 million suns worth of hydrogen all there fusing for some reason. It was just not the way galaxies are. So that wasn't working. So what do you think they turned to? The energy source of last resort, gravity. It was clear right away in this discovery in 1963 that this was a gravitationally powered source. They didn't know if it was asteroids smacking into it or some modern equivalent. They didn't know if it was collapse, but they knew it had something to do with gravity. Now remember Robinson from Texas. playing hopscotch. I think Robinson was listening to Feynman about the need for experiments, and he and his colleagues in Texas jumped on this discovery, and they held a meeting, the Texas Symposium on Relativistic Astrophysics. That's a new word there in yellow. No one had ever put those two together before because theory and experiment were separate. Robinson and his colleagues put it together and invited everybody. There's Schmidt, the discoverer of quasars. I'm going to draw attention to Thomas Gold, a famous astronomer known to have a somewhat combative personality. You see him there with a clenched fist in his discussions. But Thomas Gold brilliantly summed up the mood in the following after-dinner speech. This whole thing we're doing, he said, allows one to suggest that the relativists, with their sophisticated work, were not only magnificent cultural artifacts, but might actually be useful to science. Everyone is pleased. The relativists, who feel they are being appreciated, who are suddenly experts in a field they hardly knew existed. The astrophysicists for having enlarged their domain, their empire, by annexation of another subject, general relativity. It is all very pleasing, so let us all hope that it is right. What a shame it would be if we had to go and dismiss all the relativists again. So everybody understood that things were changing. And in fact, it was right. And this discovery launched a tremendous amount of progress. 1 year later, Penrose wrote a famous paper for which he later won the Nobel Prize. This paper put to rest theoretical doubts about the existence of black holes. Lots of papers appeared trying to explain how black holes could power these spectacular sources. Here's a fairly modern image of a quasar. There's a black hole in the middle of that galaxy, in the middle of that image, that's shooting out these particle jets, much further, much bigger than the galaxy itself, all coming from this tiny speck in the middle. And the processes by which these amazing displays were produced were understood. And some of those old mechanisms came back. Some of this is powered by stuff falling in, just as Mayer thought, stuff falling into the immense gravity of the black hole and heating up and emitting. And these jets, it's thought, were launched by matter swirling around in a circle, perpendicular to the jet. Many great discoveries were made in both theory and observation, beginning in this golden age of black hole physics and astronomy. So the two are now talking to each other, and we're at the midpoint of the story. And one of the remarkable things that happens in the second half of the story is that each also takes on a life of its own, with spectacular discoveries and surprises no one could have imagined. And so in the remaining time, I'm going to tell you a little bit about both, starting with the theory of black holes. In our list of meetings, we next check in the French Alps, Les Ouches. A new generation of scientists had been attracted to this topic of general relativity in black holes, and there was a meeting to discuss the latest physics. You see a young Kip Thorne there in the middle of your screen. Later, he will get a Nobel Prize for gravitational waves. But the names of relevance for us are Jim Bardeen, Brandon Carter, and Stephen Hawking. At this meeting, those three had some conversations and started thinking about the way the laws of mechanics look when you write them down. They found 4 laws. Remember that number? There were 4 laws of thermodynamics. They found 4 laws of what they called black hole mechanics that looked the same as thermodynamics. But there was no thermo. There's no heat, right? A black hole is a cold, dead object. Nothing can get out. It was nothing like a heat engine. And so they said very clearly in this paper, this is an analogy. It's not black hole thermodynamics, it's black hole mechanics, because there's no thermo. 2 years later, Stephen Hawking became world famous, showing that in fact there is thermo. Black holes actually radiate like anything else. The temperature is absolutely tiny. For astrophysical black holes, utterly negligible. But as a theoretical idea, it's the elephant in the room. The thing that we thought was cold and dead actually radiates. Hawking's calculation is a tour de force. He used the laws of quantum mechanics in the physical region of a black hole. and made an amazing calculation of this result. But the nice thing is there's a mechanism that I can explain to you. It has to do with, in quantum mechanics, yes, energy is conserved, that's a law, but in quantum mechanics you can borrow a little bit, okay? You can not conserve it for just a moment as long as you pay it back. And one process that's happening all the time, even in empty space, is various pairs of particles are being created and then they annihilate. This was already known. Well, if there's an event horizon, a situation can arise where one particle is created inside and the other outside. That inside particle must fall in. It can't escape. And the outside particle escapes as Hawking radiation. Now, the Hawking radiation carries some energy. That comes at the expense of the mass of the black hole. Energy is conserved. So the black hole is gradually disappearing due to this radiation. And now we have to worry not just about the fate of a star, but the fate of a black hole. This turns out to be a shockingly interesting question. And to explain why, I need cats. Okay, there's a long tradition of physicists doing thought experiments, not real experiments, thought experiments with cats. Actually, I get a lot of complaints, so there's an alternative. We're also going to use graduate students. All right, now, so you can't accuse me of anything. Only one of them is going in the black hole. The idea is, I'm not going to tell you which one. I'm doing it now. I'm putting either the cat or the graduate student in the black hole, and the other one's going back in her cage. And you're supposed to be able to tell me which one I threw in. Now, you can't tell from the picture, but we're thinking in principle in physics. How would you tell? Well, the idea, if you had asked someone this prior to Hawking's result, the answer would be yeah. Because everything's governed by quantum mechanics as far as we know. And in quantum mechanics, you can tell. Information is preserved. So we don't quite understand what's going on inside, but the idea would be if you go in there, there ought to be some way to tell. But if you have Hawking radiation, that stuff in there is getting converted to this informationless radiation. That radiation was formed at the surface of the black hole. It doesn't know anything about the inside. Now, the black hole shrinks very, very, very slowly. It takes longer than the lifetime of the universe for this to happen, for the black holes we know about. But it is shrinking. And as it does that, at least naively, it's destroying information. And when it's gone, when it has totally disappeared, leaving behind this Hawking radiation, nobody can say whether it was a cat or a graduate student. So it seems that black holes destroy information, which was a major shock and continues to be a major shock today. We call this the black hole information paradox. We have two cherished laws of physics. And when you combine them together and you ask about scales, very small like the end of that black hole, you get a contradiction. So, do black holes destroy information, or does quantum mechanics win, or is something else taking over from them both? We don't know. That was a puzzle in 1974. It remains so today, but it's been driving theoretical physics ever since. I want to tell you a little more about theory. And I'm going to jump to the present day, show you some fun surprises, some of the fun we get to have as theoretical physicists. And to do that, I need to talk about another cat, Schrödinger's cat. Schrödinger was one of the early pioneers of quantum mechanics. And in quantum mechanics, this is actually well understood. An elementary particle, say, doesn't have to be just here or just there. It can be in a state where it has some probability of being in both places, which we think of it as being in both places at once. And Schrödinger pointed out that, yes, we know this is true for elementary particles. We have experiments. But it should also, therefore, be true for larger objects that you could build. And he described a thought experiment whereby coupling a vial of poison to some elementary particle, quantum thing, a cat ends up in a state that's both alive and dead. Now, I'm guessing you've never seen a Schrödinger cat sitting in front of a couch. And that's because it's being bombarded, if it were out there, by all sorts of external influences that degrade the quantumness. Another way of saying that is if you measure the cat, it picks one. So you need to put your Schrodinger cat in a box. You could imagine ordering this box from Amazon. It would probably have better spelling than the AI art. But it would come in a box, and the cat would be in its superposition of alive and dead. And when you open the box, then it picks one. So that's the way Schrodinger's cat works, and it's been with us since Schrodinger in the 1930s. Now I want to tell you about a very interesting paper that came out just over a year ago that I've been working on follow-ups to enthusiastically. Again, these authors did a calculation, but again, there's a great mechanism. And the idea is, well, normally you degrade the quantumness of that cat by opening the box, and it gets bombarded by stuff. But you could also measure the cat from outside if you measured its gravity. So bear with me. These authors thought, all right, if the cat's breathing, it has different gravity. If it's, you should be able to tell from its gravitational field which state it's in. And so by measuring the gravity, you can degrade the quantumness of that cat state. One step further, guess what's coming? We're going to go inside a black hole. Instead of doing the measurement right next to the box, we're going to do it from inside a black hole. Now, the cat can't learn about you if you jumped in the black hole. You can't talk to the cat, but the cat can talk to you. He can send stuff in, and his gravitational field penetrates the black hole. So you can measure the cat. You can degrade the quantumness from in the black hole. Okay, only one more step. Stay with me. You can follow this. The last step is realizing that nothing you do in the black hole can actually affect the outside. So if somebody could have gone in and done this measurement, it means the black hole has to be doing the same thing all by itself. Just going near the black hole has to degrade the quantumness of that state. So black holes just passively destroy quantum coherence. A more tangible way of thinking about this, we hear a lot about quantum computing. Quantum computers are devices that use Schrodinger cat-like states as a computing resource. They need to keep those states coherent, isolated from their environment. That's how they work. You don't want to bring one of these near a black hole, we learned just a couple years ago. The black hole wipes the quantum information clean from the memory banks of the computer. I found this incredibly shocking. I knew that information was destroyed if you throw stuff in, but the black hole is just destroying information around it just by sitting there. I don't know what this is teaching us about the nature of reality, but it feels really deep, and so I've been working enthusiastically on this topic. So that's my tour through the theory of black holes, from Hawking shocks to the little aftershocks like the one I just mentioned. In the last 15 minutes, I'd like to tell you the story of observing black holes. Black holes have been observed in a variety of ways, from the radio galaxies, the quasars we mentioned. There are smaller black holes that have matter falling into them, which heats up and emits X-rays. You can see orbiting stars around the black hole in our own Milky Way. And our poem was about gravitational waves from black hole mergers. On the right of your screen, we had a Nobel Prize for both of those topics. 2 Nobel Prizes. If you followed the field, you'd know I'd left something out. There's a spot here for a picture of a black hole. And before I show you that, I think it's useful if we all together do a little warm-up exercise. I want everybody to think, what does a black hole look like? Now, I work on this topic, and I put a lot of work into it. And I'm going to show you an image from my group. And I'm not saying you need to clap and cheer raucously and have a celebration when I show it to you, but at least internally, show some appreciation. All right, ladies and gentlemen, without further ado, this is what a black hole looks like. Okay, at least I've hopefully woken you up now. So, black hole's not emitting anything. A couple Hawking photons, quanta, whatever, you're not going to measure it. Okay, when we ask what does a black hole look like, we need it to be illuminated by something. And I'm going to focus on one kind of illumination, which is you're going to have a disk of matter, plasma really, swirling around it. And you're looking at this disk face on. So it looks like a donut. This is a theoretical model. And look at that, black hole. It's actually a very good name. If the black hole is illuminated by something that's at least not right in front of it, you will see a black hole because the black hole isn't emitting. It will look dark. We've got hot plasma swirling around it. That's what produces the emission ultimately. And there's a feature it may be hard for your eyes to see that I'm going to guide with a little animation here. There's a ring of light. As I remove this little dashed circle, see if your eyes can stay on that ring of light. That light is called the photon ring. Believe it or not, that's the back of the disk. That's light that was emitted backwards, but at just the right angle so that the black hole's strong gravity actually bent the light around and back to the camera out front. These three features are going to be present in every black hole image we'll look at. And let me tell you the story of going out and observing. The story actually starts way back in 1918. In fact, the first black hole observer I've been showing you this picture might be Heber Curtis, who had a new telescope and just looked at everything interesting. And it's great to read these old papers. There's no pictures in there. You didn't publish your pictures in those days. It's just words. 762 things he looked at, a sentence or two about each. And one of them, he says, he saw a curious straight ray. That was one of those jets of particles. And that one that Curtis saw turns out to be the very best black hole to go try to photograph. Now, I've jumped forward to around the year 2000 when people first started thinking about actually imaging a black hole. Some of that work was actually done right here. The paper that started it all, one of the co-authors was Fulvio Melia in the Department of Physics. And in the year 2000, this was the state of the art for observing this source. There's a black hole at the center, there's this jet of particles, and you can see in the lower right that we've resolved the jet launching region, but the black hole is much smaller. There should be a little dark spot somewhere in that image. So it's a factor of 10 resolution increase, but that's not totally crazy, and people started thinking about maybe we could do this. I had E equals mc squared in the talk. Now I'm going to give you the second equation, which is going to tell us how we're going to get higher resolution. The equation is bigger telescope equals better resolution. So the images I showed you on the previous slide were from networks of radio dishes working together as one telescope. First co-located radio dishes, the VLA, and then radio dishes spread out over the continent of North America. So we have to go even bigger. And the idea was born for a global telescope, the Event Horizon Telescope. In the first observations, there were 8 stations. Arizona was heavily involved in the observational effort and some of the theory as well. And before I show you the image, let me tell you a little bit about how this measurement is made. So light is a wave. It has peaks and troughs like any other wave. And in radio astronomy, you point your dish, and what you get is some wiggles in the voltage of your receiver. That's representing the sum of all the light coming from all the different sources in your field of view. Now, it's hard to make an image with a single telescope. You can kind of point it around a little bit. But there's a trick where if you have more than one, you point them in the same direction. And if you think about one little element in that galaxy, it's fluctuating randomly. And those random fluctuations are carried out in these wave fronts of the wave. And both telescopes receive the same random fluctuations from that point. So somewhere buried in the signal you get in the two telescopes is a correlation, a part of that signal that's very similar. And you can dig that correlation out by a kind of embarrassingly simple process of just multiplying the two signals together and time averaging. So there's 3 steps in radio astronomy making an image this way. The first thing you need to do is record the signals. These telescopes are often in very beautiful places. This one's at the top of a ski hill. You could get your skiing and your observing in one day. And the Event Horizon Telescope team deployed new receivers, new clocks, a whole electronic setup to equip these telescopes to work together. You need a lot of hard drives to record the data. It's like 60 gigabits or something. You're filling up, a terabyte hard drive and over very quickly, a few seconds. It's a little more than that. Here's the clock. It doesn't look like your clocks. It's big. It's a hydrogen maser. You really need to track time accurately to do these measurements. You get all this data, all these telescopes around the globe looking at the same source at the same time. You need to send it back to a central location to be correlated. So you might think, all right, we'll store it on the cloud, Amazon Web Services, Box. No, not fast enough. You need the world's fastest internet connection, which is a plane full of hard drives. So you get all that data, 3.5 million gigabytes roughly in the first observations. You fly it to MIT, where they have a powerful machine built just for this purpose. And after correlating, you get some text files out. Here's a shot of my computer. You might be able to see the sizes, 500 kilobytes. It's an amazing, amazing feat of pulling out a small amount of information from a huge mountain of data. But it's just the information you need. The last step is to turn this into an image. The team did an excellent job. They invented new techniques. Rather than tell you the details, I think let's just watch and see what they got. It's a truly beautiful image. And amazingly, it's got all the features we expected. There's the black hole. There's the hot plasma swirling around it. We don't have a photon ring yet. And that's what I'm going to tell you about next. It's brighter on the bottom. That has to do with the Doppler effect. That was expected too. A component of the matter on the bottom is actually moving a little bit towards you, because this donut is tilted a little bit towards you. And the Doppler effect makes it look brighter. So now we can put our black hole image back in the beautiful screen of black hole observations. It's tempting just to look at it and think how beautiful, but of course, this is science. We need to ask, what did we learn? Well, the black hole was confirmed. We see the black hole. There was really strong evidence it had to be there, but in a field like this, you want to always be looking for consistency. Furthermore, it has the expected mass. It matches other measurements of the mass. Really exciting to me was the confirmation of this idea that the matter is swirling around perpendicular to the jet. That's what's supposed to help launch that jet, and it being brighter on the bottom is exactly where it should be brighter, given the orientation of the jet. And finally, and exciting for the future, is boy, is this a really nice source. Higher resolutions of this source would be incredible. And here's an image from my group. This is the image, but now I'm going to show you what we think it might look like if observed at higher resolution. We think that blurry image would turn to an image with sharp ring-like features. These are these photon rings I told you about. The reddish blur you mostly see, that's the front of the disk. That's the hot plasma emitting light right towards you. But then this ring here, that's actually the back of the disk. Light coming off the back of the disk that got captured and orbited the black hole and came back to the camera. And there's another ring, the front of the disk. This is light that came off the front, but not right at you, at a kind of angle, so that it was captured by the black hole and went around it the whole time and came to you. And in principle, there's infinitely many of these things. So in principle, when you look at the stuff near a black hole, you actually see infinitely many copies of it. Quite mind-blowing, but wouldn't it be amazing to just resolve even the first one? So how are we going to do that? Bigger telescope equals better resolution. We've already used up the size of the Earth. What can we possibly do? Well, got to go to space. That's how we'll get a bigger telescope. So I'm part of a mission proposal in progress called the Black Hole Explorer. Next week, in fact, I'll be at a collaboration meeting for the Black Hole Explorer. We really need to figure out, iron down those mission requirements for that proposal to go in next year to NASA. So I won't be here next week, but you definitely should, because next week we have an amazing talk from Charlotte. I've seen the talk. I wish I could be here. It's so much fun and so informative. So come learn about tree rings on Valentine's Day next week. Bring your date. But today, we're going to finish up with photon rings. Now, it's nice to just stare at the image and think, how beautiful. But, as always, this is science. We need to ask. We certainly need to tell NASA what we're going to do with it. There are many science cases involving astrophysics and fundamental physics. For my money, the one I'm most passionate about is testing the laws of gravity with this observation. Einstein's theories of gravity have been tested very precisely in a number of regimes, but we know they have to break down at some point because of things like the information paradox and so forth. Any clue we can have from observations would be amazing. So my collaborators and I made the following proposal a few years ago. Building on some other work, we realized that although making a really sharp image would take a whole swarm of satellites, that's too expensive, just one extra satellite can help us measure the diameter of this photon ring, find out that it's there, and measure its diameter. Not only that, we think we can measure the diameter separately at each angle, so we get a shape. This is interesting because the theory of relativity, Einstein's theory, makes a prediction for the shape. So I've shown you a mock data analysis of a mock experiment where things match. The orange curve is the prediction, and the data match it. When we get a real experiment, the Black Hole Explorer, and for something this precise, one of its successors, we will be able to make the same plot. And if it matches, terrific. Einstein passes the test. If it doesn't match, then we have a really exciting hint of what could be the next deeper layer in gravity that could maybe help resolve some of the puzzles I've told you about today. Let me summarize. Today we worried about the fates of stars and black holes, and the fates of cats and graduate students. And I took you on a tour, a whirlwind tour, but hopefully an enjoyable one, of the beautiful and spectacular astronomical displays that these monsters of gravity produce for us. These monsters of gravity, these giants of the universe, nevertheless have upended everything about our understanding of physics at the smallest possible scales. What an exciting situation. There's been a lot of progress, so much understood, but of course many mysteries remain. I don't know what the future will hold, but I do know that there will be surprises. Thank you very much for your attention, and good night.
Let's have one more round of applause for Sam Gralla tonight. Thanks, Sam. So I would like to invite all of you to next Wednesday's lecture series presentation, as Sam gave us a little bit of a preview, featuring Dr. Charlotte Pearson from the Laboratory of Tree Ring Research. Charlotte is going to share a little more about her talk for next week on Valentine's Day.
Hi, my name's Charlotte Pearson. I'm an associate professor here at the Laboratory of Tree Ring Research at the University of Arizona. And I hope you enjoyed Sam Gralla's really fascinating talk tonight. And I hope that perhaps I can persuade you to come out next week at the same time to listen to a talk about how tree ring science was invented and the amazing things that trees can tell us today, and also some of the fantastic exploration that I think is going to be possible through tree rings as we move into the future. So we hope to see you here this time next week. Thank you.
Well, again, we hope to see you next Wednesday evening as we share our love for science on Valentine's Day and hear more about the fascinating research happening in the Laboratory of Tree Ring Research. We will have sweet treats provided by Whoops Bake Shop for the first 500 guests next week, so make plans to join us for Charlotte's talk. So thanks again for joining us tonight. Please get home safely. Good night.